Welcome to this video on the Propagator, focusing on mastering time evolution operators, the engine of quantum dynamics. I'm Julia. Quantum states are dynamic. They ripple and change as time passes. We need a mathematical tool to bridge the present and the future of a quantum system. This tool is the time evolution operator, essential in our search for motion. The time evolution operator is the mathematical machine that moves our system along the timeline of Hilbert space. Our goal is to find the final wave function at time t, starting from the initial state at time 0. We begin with part 01, the definition, where we establish the operator u. Introducing u, we define the operator such that it acts on the initial ket vector at time 0 to produce the ket vector at time t. It serves as a map connecting states across time. Because the Schrödinger equation is linear, our evolution operator must also be linear. This is crucial for superposition. States evolve independently and combine correctly in the future. For the initial condition, at time 0, the operator must equal the identity operator. Physically, this means that if no time has passed, the system remains exactly as it started. To preserve probability, the total probability must always be 100%. Therefore, the operator u must be unitary to ensure the system doesn't lose or gain probability. The unitary condition requires that u dagger, the conjugate transpose, multiplied by u, equals the identity. This ensures the length of our state vector remains constant as it rotates through Hilbert space. We move on to part 02, the derivation, where we connect the operator u to the Schrödinger equation. Step 1. The master law begins with the time-dependent Schrödinger equation. This equation shows that the rate of change of the state is proportional to the Hamiltonian, which represents the total energy. Step 2. Substitution involves plugging our definition of the future state, as u acting on the initial state, into both sides of the master equation. This helps us focus on the operator's evolution. In step 3, isolating the operator, since the initial state is constant, the derivative ignores it. We are left with a differential equation, where the rate of change of u is directly determined by the Hamiltonian. Step 4, the differential form is achieved by rearranging the equation. Dividing by I times h bar reveals that the operator's evolution is proportional to the system's energy, a first-order differential equation. In step 5, the integration, if the Hamiltonian is constant, the solution is an exponential function. This fundamental result defines the time evolution operator for stationary systems. Now we examine part 03, the interpretation, decoding the physical reality of the time evolution operator. The Hamiltonian is the generator of time, acting as the engine of quantum dynamics. Just as momentum generates translations in space, energy generates translations in time by rotating the wave in the complex plane. Unitary evolution is a state rotation. The operator u changes only the direction of the state vector in Hilbert space, preserving its size. This is why it is called unitary. It preserves the unit length of the probability vector. In the stationary case, if we are in an energy eigenstate, the operator simply adds a rotating phase factor. The physical probability density remains unchanged, confirming these are stationary states. Evolution steps are additive. Moving from time 0 to time t2 is the same as moving sequentially through intermediate times. This group property ensures the system's history is continuous and consistent. Part 04 covers the Schrödinger picture, which distinguishes between evolving states and evolving operators. In the Schrödinger picture, the operators remain fixed, and only the state vector, psi, evolves using the time evolution operator. This is the common way to visualize quantum mechanics. To calculate averages, we sandwich the operator between the evolved state and its conjugate. This calculation shows how the unitary rotation of the state influences our physical measurements. The operator is unitary, meaning the inverse time evolution is just the conjugate transpose. This perfect memory implies quantum evolution is reversible. The starting point can always be mathematically retrieved. We conclude with part 05, the impact, exploring how this theory translates to quantum technology. Quantum gates are unitary gates. Every quantum gate is essentially a time evolution operator. Future computers control the Hamiltonian precisely to evolve qubits into the desired answer without data loss. In recap, u is the map connecting states across time, derived from the Schrödinger equation. It must be unitary to conserve probability and is reversible and deterministic in nature. Finally, we have part 06, a deep dive into the properties of the time evolution operator. Unitary operators preserve the angle and distance between states in Hilbert space. This logical consistency ensures that distinct information is never blurred during quantum evolution. The eigenvalues of U have an absolute value of 1. They only affect the phase and do not change the magnitude of the states, confirming phase eigenvalues are essential to the operator's function. Constants of motion exist when an operator commutes with the Hamiltonian. This means the property is a conserved quantity, and the time evolution operator will not change its expected value. The Heisenberg contrast is an alternative view. Here, the state vector is static, and the operators themselves evolve using U. Both pictures yield the same physical results. For a free particle, the operator U causes spreading waves, where the wave packet naturally diffuses in space. This is the physical manifestation of the uncertainty principle over time. Because unitary evolution is reversible, information survival is guaranteed. The entropy of a pure isolated quantum state is always zero, meaning information is never truly lost.